Today we'll be talking about what a manifold is. First off, we'll start off of the definition of a manifold. A manifold is a mathematical space that when you zoom in close enough around any point, it looks like an ordinary Euclidean space. Euclidean space is a flat space described using coordinates such as r to the power of 1, a straight line, r to the power of 2, a flat plane, r to the power of 3, ordinary flat 3D space, and here you'll find a straight line, which is commonly found in middle and high school classes. R to the power of 2 is the x and y axis and is a flat plane. R to the power of 3 is an ordinary flat 3D space, which is x, y, and z. Here you'll find the equation of a sphere and the model of a sphere, of course. And here you'll find the equation of the mapping notation. And here it's red. Phi maps u into the real plane. Here, phi gives points coordinates. U is the piece of the manifold we're looking at. The arrow is the direction of the mapping, and R2 is a flat 2D coordinate plane. Next, we'll look at an example. Consider the surface, the set of all points x, y, and z in three-dimensional real space such as x squared plus y squared plus z squared equals 1. The question here asks, why is s to the power of 2 a two-dimensional manifold even though it's contained in the three-dimensional space r to the power of 3? Well, the sphere is contained in r to the power of 3, which is the third-dimensional space, so it exists in the three-dimensional space, obviously. So we'll take a look at the surface locally. We'll zoom in on the small neighborhood U of the sphere. Locally, the curved surface looks like a flat two-dimensional plane. Mathematically, we can describe this with a coordinate plane, phi u, and then arrow r. This means we can use two coordinates to describe a small part of the sphere. Our third step and final step is to state the dimension. Since the sphere locally looks like r to the power of 2, then dimension of s to the power of 2 equals 2. Or the answer is s to the power of 2 is a two-dimensional manifold because locally its surface looks like r to the power of 2 even though it's contained in r to the power of 3, and only two independent coordinates are needed to describe its surface locally. Here is a pretty cool example of how this is the surface, or the Earth, and the neighborhood is the little patch that we're taking a look at. Next, consider the surface, and then the same equation as we saw earlier. In the North Pole, P is equal to 0, 0, 1. Find the tangent space. Find the tangent space T sub P s squared. North Pole P equals 0, 0, 1. Find the tangent space T sub P s squared. First, we'll start with the sphere equation. X squared plus y squared plus z squared equals 1. And then we'll move everything to one side, which gives us f x y z equals 0. The sphere is a set where... So in English, we'll create a function f whose zero set is the sphere. Next, we'll take the partial derivatives and the gradient. And here you'll just do that, and it's pretty self-explanatory. Therefore, delta f is equal to 2x, 2y, 2z. And in English, the gradient gives us a vector perpendicular or normal to the sphere. Our third step here is by substituting p into the gradient, and we'll multiply everything here by 0, and we'll multiply everything here by 0. We'll multiply everything here by 2, 2, and 1. So at the North Pole, the normal vector points straight towards the z direction, which is up and down. Step 4, over here, let v be the tangent vector. V equals ABC. and v to be tangent to the sphere, it must be perpendicular to the normal vector. So in English, a tangent vector must be perpendicular to the normal vector. On step 5, we'll use the dot product, and we'll substitute the vectors ABC times 0, 0, 2 equals 0. And then we'll calculate, which will give us 0, and then will give us 2c equals 0. Therefore, c equals 0, and we can then substitute that in. So it will give us the tangent space of S squared at the North Pole. P consists of all vectors with arbitrary x and y components, but a z component of 0. In other words, it's the horizontal plane tangent to the sphere of the North Pole.